Okay guys, this is a continuation of our last video. We left off after doing number 8. Sorry, I didn't mean to cut that video off, but I had to go help bring in some groceries. We'll just pick up here at number 9 is a example problem, so I'm not going to do it. But these problems in like number 10 and 11, 12, 13, and 14, they look complicated and they are difficult because they're the same type of idea as numbers 1 through 8, but they throw in variables here. So we have to treat the variables as if they're numbers. So I'll show you how to do this when we start with number 10. First thing we're going to do is we're going to focus just on 484 first. So we're going to see whether we can break down the square root of 484. And actually, the square root of 484, it's a perfect square. So it actually is just 22. So I don't need to do anything fancy. I can just know that the 22 is going to come outside of the square root. And then left underneath, we have b to the third. Now b to the third is not a perfect square because it's an odd exponent. If the exponent was even, then it is a perfect square. So what we're going to do is we're going to just rewrite b to the third as b to the second, which is even, times b to the first, or just b. When I do this, I'm allowed to break this up, and we can take the square root of b squared. The square root of b squared is just b, so I have 22. I have b, and then what's left underneath the square root is the b that I couldn't do anything with. So my final answer here is 22b times the square root of b. So similar process as before, we just have to treat the variables as if they were numbers and be able to break up the exponents into an even exponent times the odd exponent. So if you look at number 11, it's similar. We have the 3 already on the outside. We're not going to touch that. But we're going to break down the inside. 99 is not a perfect square, but 9 is. So we can say 9 times 11 is equal to 99. X to the 5th is not a perfect square, but x to the 4th is. So we can say x to the 4th times x. And then y can't be broken down because it's just y to the 1st. So when I do this now and I start thinking about how this works, I'm going to keep the 3 on the outside. But now I'm going to add another 3 because the square root of 9 is 3. We're going to add 11, we can't take the square root of, so it's going to stay under the root. X to the 4th, the square root of that is x squared. So we just divide it by 2 basically. And then we're done because the rest can't be simplified. So what we have underneath is we have the 11 that I couldn't do anything with, and we have the xy which I couldn't do anything with. When I simplify this, 3 times 3 gives me 9. I have 9x squared times the square root of 11xy. So once again, the idea is to break down the numbers and the variables into expressions that I can take the square root of and expressions that I can't. The things I can take the square root of, I go ahead and do that and bring them outside of the square root. The things I can't take the square root of, I leave underneath of the square root in my final answer. So using that theory, again, we're going to move on to number 12. So I look here on the next page at number 12. We're going to break all of these things down as usual. So the first thing we're going to do is we're going to notice that 525 breaks down into 25 times 21. So we're going to break that up. 25 is a perfect square. That goes in there. Right? A to the 7th, not a perfect square, but a to the 6th is. So a to the 6th times a will work. B to the 6th is already a perfect square, so I leave it alone. C to the 17th is not, so I go C to the 16th times C. The idea here is to pick the even number that's closest to the original number. So if I have 17, I'm always picking one less 16. If I had 29, then I would pick 28. Right? You always pick the one that's closest to that odd number and go from there. So now I'm going to break this down. I take the square root of 25 and I get 5. I take the square root of a to the 6th and I get a to the 3rd. I take the square root of b to the 6th and I get b to the 3rd. Take the square root of c to the 16, I get c to the 8th. The stuff that's left that I didn't touch, like the 21, this a, and this c, stay underneath of my square root, and I'm finished. Once again, you also hear me say that a square root symbol is called a radical, so you need to get used to that terminology when we move forward with this stuff. 13, similar process. I'm going to break down the 108. So I break that down into 36 times 3. 36 is a perfect square. I break down the x to the 11th into x to the 10th and x. Now I take the square root of what I can take the square root of. So the square root of 36 is 6. It comes out. The square root of x to the 10th is x to the 5th. I divide by 2. And then I leave underneath the 3 that I didn't touch and the other x that I didn't touch. And my problem is now solved. Similarly for 14, I'm going to look at 661. 661 is actually a prime number, which means that it has no other factors except itself and 1. So I can't break it down, so I just have to leave it 661. W to the 4th I'm going to leave because I'm going to be able to take the square root of that. And then I'm going to break down x to the 13th into x to the 12th times x because we want that even number. And then when I do this, I can take the square root of w to the 4th, it's w squared. I can take the square root of x to the 12th, which is x to the 6th, but I can't take the square root of 661, so it stays underneath of the radical, and I can't take the square root of this last x. So when I do that, I come up with my final answer, which is w squared times x to the 6th, all times the square root of 661x. This ends our set of videos for the summer packet. I know there's some other pages in this packet, but they weren't exactly easy to make videos for. So what I ended up doing was posting the answer key for those pages online. So you should check out Schoology. If you have any problems with that, just let me know. Come in for some extra help. We'll get it taken care of. Thanks, and I'll see you soon.